Learning objectives. In this chapter, the user would learn the following in detail. Introduction to printed circuit board, PCB manufacturing process, types of PCB, single-sided, double-sided, multi-layer and flexible. Fabrication process for single-sided PCB, double-sided PCB, multi-layer PCB. Soldering procedure. Repair of PCBs. Design rules for schematic drawings. Design considerations. Layout planning and routing rules. Study of documentation in design and fabrication. PCB design rules. PCB design using CAD. Study of IPC standards. Design rules of schematic diagram. Schematic diagram. A schematic or a schematic diagram is a representation of the elements of the system using abstract graphical symbols rather than realistic pictures. A schematic usually omits all details that are not relevant to the information. It is intended to convey and may add unrealistic elements that aid comprehension. A schematic diagram of a chemical process uses symbols to represent the vessels, piping, valves, pumps, and other equipment on the system, emphasizing their interconnecting parts and thus suppressing physical details. In an electronic circuit diagram, the layout of the symbols may not resemble the layout in the circuit. In the schematic diagram, the symbolic elements are arranged to be more easily interpreted by the viewer. A semi-schematic diagram combines some of the abstraction of a purely schematic diagram with other elements displayed as realistic as possible for various reasons. It is a compromise between a purely abstract diagram, example, the schematic of the Washington Metro, and an exclusively realistic representation, example, the corresponding aerial view of Washington. Rules. Wires connecting are indicated by a heavy black dot. Wires crossing but not connecting have no dot. 4 wires must not connect at a point, that is, wires must not cross and connect. Always use the same symbol for the same device. Example, do not draw flip-flops in 2 different ways. Exception, assertion level logic symbols show each gate in 2 possible ways. Wires and components are aligned horizontally or vertically unless there is a good reason to do otherwise. Label pin numbers on the outside of a symbol. Signal names on the inside. A schematic diagram must provide a broad view of design with all components. It gives visibility into the status of all parts of the design process. It is the primary source for developing deliverable steps for producing design and manufacturing steps. Design variants are designed around slightly different schematics. Test departments rely on schematics. Field services rely on schematics. Bill of materials are generated from schematics. Guidelines. Guidelines are developed over the years of drawing schematic. Main features of guidelines are: signal flow moves from left to right across the page with inputs on the left side and outputs on the right side. Electronic potential should increase as they move from bottom to the top of the page. Use unit number for assigning a unique IC packaging identification. Introduction to printed circuit board. What is PCB? Printed circuit board, PCB, or printed wire boards electrically interconnect all the components, mechanically support to the components, non-conductive substrate. It dissipates heat generated by the components. PCBs are rugged, inexpensive, and can be highly reliable. Printed circuit boards are called as printed wire boards. Printed circuit boards base for physically supporting and wiring the surface mounted and socketed components in most electronics. Why PCB boards are green? Green color indicates that it is made from glass epoxy, which is naturally green. PCB could be made in every single color that exists. The finishing color is usually a soldered mask. This mask is applied for safety reasons for preventing eventual short circuits. Advantages of PCB. There are many reasons for using PCB instead of other interconnection methods and component mounting techniques. The size of the component assembly is reduced. Quantity production is achieved at lowest unit cost. Circuit characteristics are maintained without introducing variation in inter-circuit capacitance. They ensure a high level of repeatability. Inspection time is reduced because printed circuitry eliminates the probability of error. Chance of miswiring and short-circuited wiring are minimized. Evaluation of printed circuit board. The first printed circuit board PCBs can be traced all the way back to the early 1900s and a patent for printed wire. It was in 1925 that Charles Dukas first submitted a patent that involved creating an electrical path directly on an insulated surface. It was a revolutionary idea because it could eliminate complex wiring and provide consistent results. Still, they did not really catch on until after World War II, when Dr. Paul Eisler in Austria began making the first real operational printed circuit boards in 1943. Before printed circuits became the common component used in electronics, point-to-point construction was used. This meant some extremely bulky and unreliable designs that required large sockets and regular replacement. Most of these issues were directly addressed when PCBs went into regular production. 1920s, the early PCB material could be almost anything, from bakelite and masonite to plain old thin pieces of wood. Holes could be drilled into the material and flat brass wire would be riveted onto it. It may not have been pretty, but the concept was there and it worked. It was often used in radios and gramophones at the time. 1947. First double-sided PCBs with plated through holes produced. 1950s to 1960s. The types of material used for the board were shifting to different resins and other materials, but they could still only be printed on single side. The wiring would be printed on one side and the electrical components would be on the other. Still, it was much more efficient option than bulky wiring, so it was starting to see a wider adoption. One of the biggest steps forward came in 1956 when the US Patent Office granted a patent to a small group of scientists representing the US Army for the process of assembling electrical circuits. At the time, the process involved drawing the wiring pattern and then photographing it onto a zinc plate. This plate could then be used to create a printing plate for an offset printing press. This is what was used to print the wire in acid-resistant ink on copper foil, which could then be etched by an acid solution. 1957, IPC, the Institute of Printed Circuits, formed and held first meeting in Chicago, Illinois. 1960s, multi-layer 4-place layer count PCBs began production. 1960s to 1970s. Boards were designed using 4:1 red and blue line vellum method for hand tapping components and tracks. A precision camera then produced the 1:1 negative manufacturing film. An experienced designer could lay out and tape a board at the rate of about 2 hours for each equivalent 14-pin IC on the board. 1970s. The circuitry and overall size of the boards were starting to get a lot smaller by the 70s, and a hot air soldering methods began to be used. This is also when the Japanese developers began to create screen processes that used various aqueous developed LPIs liquid photo-imageable masks. This became the industry standard over the years. 1980s. Surface mount parts became the preferred option over through-hole components, which led to further size reduction while maintaining the same level of functionality. 1986. RS-274X released as an enhancement to RS-274D data format. New version supports embedded aperture information, relieving the need for external aperture definition files. 1992. Valor Computerized Systems founded, introducing Genesis 2000 software for PCB, CAM and DFM. 1990s. While the complexity of modern circuit boards continues to go up, the size of boards and the cost of material has generally been able to go down. Once developers were able to start components of printed circuit board are base, which is a thin board of insulating material, rigid and flexible, which supports all conductors and components. The conductors, normally of high purity copper in the form of thin strips of appropriate shapes, firmly attached to the base material. Base. The base provides mechanical supports to copper areas and all components connected to the copper. The electrical properties of the completed circuit depends upon dielectric properties of the base material. The conductor, not only providing electrical connections between the components, it is also used to solder attachment points for the same. When the completed board provides mechanical supports to the electrical connections to the components, it is essentially known that printed circuit board or printed wiring board. PCB characteristics. Through-hole technology. The first PCBs are used through-hole technology, mounting electronic components by leads inserted through holes on one side of the board and soldered onto copper traces on the other side. Boards might be single-sided with unplated component side or more compact double-sided boards with components soldered on both sides. Horizontal installation is done by bending the leads 90 degrees in the same direction, inserting the part in the board, soldering the leads and trimming off the ends. Leads may be soldered manually or wave soldering machine. Through-hole manufacture adds to board cost by requiring many holes to be drilled accurately. Limits the available routing area for signal traces on layers immediately below the top layer on multi-layer boards, since the holes must pass through all layers to the opposite side. Once surface mounting came into use, small size SMD components were used where possible, with through-hole mounting 1/10 of the size and weight of through-hole components and passive components much cheaper. Price of semiconductor surface mount devices of components not suitable for surface mounting. A box of drill bits used for making holes in printed circuit boards. While tungsten carbide bits are very hard, they eventually wear out or break. Making holes is considerable part of the cost of through-hole printed circuit board. Surface mount technology. Components are mechanically redesigned to have small metal tabs or end caps that could be soldered directly onto the PCB surface instead of wire leads to pass through holes. Components became much smaller. Component placement on both sides of the board became more common than with through-hole mounting. It allows much smaller PCB assemblies with much higher circuit densities. Surface mounting lends itself well to a high degree of automation, reducing labor cost and greatly increasing production rates. Components can be supplied mounted on carrier tapes. Surface mount components can be about 1/4 to SMDs are determined more by the chip itself than the package, with little price advantage over large packages. Challenges in modern PCB design and manufacture. Main stages in electronic product development are shown in figure. Concept. It defines specifications, requirements, and overall architecture of design. Capture. Defines design intent by describing its functionality. Layout. It determines placement of components and routing. Above steps leads to hardware prototype and manufactured item released into market. Not long ago, designers used pencil, pen, paper to design a circuit and layout. Nowadays, AutoCAD design were developed to make easy circuits. When subsystems are assembled together, it leads to complex in single board. Today's electronic system require to increasing fast, small, low power, lightweight components. Clock frequency and signal speeds are rising dynamically. It leads designer to design AutoCAD and EDA tools. Major markets drive for PCB industry. Complexity or performance, form factor or size, reliability or quality, time to market or cost. IPC Standard. IPC, Association Connecting Electronics Industries. A trade association whose aim is to standardize the assembly and production requirements of electronic equipment and assemblies. It was founded in 1957 as the Institute for Printed Circuits. Its name was later changed to the Institute for Interconnecting and Packaging Electronic Circuits to highlight the expansion from bare boards to packaging and electronic assemblies. In 1999, the organization formally changed its name to IPC with the accompanying tagline, Association Connecting Electronics Industries. IPC is accredited by the American National Standard Institute (ANSI) as a standards developing organization and is known globally for its standards. It publishes the most widely used acceptability standards in the electronics industry. Standards. IPC standards are used by the electronics manufacturing industry. IPC A610 acceptability of electronic assemblies is used worldwide by original equipment manufacturers and EMS companies. There are more than 3,600 trainers worldwide who are certified to train and test on the standard. Standards are created by committees of industry volunteers. Task groups have been formed in China, the United States, and Denmark. General documents. IPC T50 Terms and Definitions. IPC 2615 Printed Boards Dimensions and Tolerances. IPC D325 Documentation Requirements for Printed Boards. IPC A31 Flexible Raw Material Test Pattern. IPC ET 652 Guidelines and Requirements for Electrical Testing of Unpopulated Printed Boards. Design Specifications. IPC 2612 Sectional Requirements for Electronic Diagramming Documentation, Schematic and Logic Descriptions. IPC 2221 Generic Standard on Printed Board Design. IPC 2223 Sectional Design Standard for Flexible Printed Boards. IPC 7351B Generic Requirements for Surface Mount Design and LAN Pattern Standards. General Documents. IPC T50 Terms and Definitions. IPC 2615 Printed Boards Dimensions and Tolerances. IPC D325 Documentation Requirements for Printed Boards. IPC A31 Flexible Raw Material Test Pattern. IPC ET 652 Guidelines and Requirements for Electrical Testing of Unpopulated Printed Boards. Design Specifications. IPC 2612 Sectional Requirements for Electronic Diagramming Documentation, Schematic and Logic Descriptions. IPC 2221 Generic Standard on Printed Board Design. IPC 2223 Sectional Design Standard for Flexible Printed Boards. IPC 7351B Generic Requirements for Surface Mount Design and Land Pattern Standards. Material Specifications. IPC FC 234 Pressure Sensitive Adhesives Assembly Guidelines for Single-Sided and Double-Sided Flexible Printed Circuits. IPC 4562 Metal Foil for Printed Wiring Applications. IPC 4101 Laminate Pre-Preg Material Standard for Printed Boards. IPC 4202 Flexible Base Dielectrics for use in flexible printed circuitry. IPC 4203 Adhesive Coated Dielectric Films for use as cover sheets for flexible printed circuitry and flexible adhesive bonding films. IPC 4204 Flexible Metal Clad Dielectrics for use in fabrication of flexible printed circuitry. Performance and Inspection Documents. IPC A 600 Acceptability of Printed Boards. IPC A 610 Acceptability of Electronic Assemblies. IPC 6011 Generic Performance Specification for Printed Boards. IPC 6013 Specification for Printed Wiring, Flexible and Rigid Flex. IPC 6202 IPC/JPCA Performance Guide Manual for Single and Double-Sided Flexible Printed Wiring Boards. PAS 62123 Performance Guide Manual for Single and Double-Sided Flexible Printed Wiring Boards. IPC TF 870 Qualification and Performance of Polymer Thick Film Printed Boards. Layout Planning and Routing Rules. Layout Planning and Design. It clearly defines all details of the circuit. The detailed circuit diagram is very important for the layout designer, and designer must be familiar with the concepts of design. General considerations for layout. Layout scale. Depending on the accuracy required, the circuit would be produced at 1:1 and 2:1. It offers a reasonable compromise between accuracy gain and handling convenience. Grid system. The use of grid system in layout is commonly accepted practice. Components are manufactured with lead with grid intersections, and numerically controlled drilling equipment can be easily programmed accordingly. For the layout designer, for the use of grid gives more convenience in the placement of conductors and components. PCB production facilities. Limitations in layout are minimum and maximum boarding size, table size, drilling accuracy, fine line etching process, etc. Limitations should be considered in PCB design because it is an essential. Designer should spend certain amount of time in PCB design process. Standards. Standards are laid down to achieve repetitive results of satisfying specified requirements. Standardization can be introduced at any level for any purpose. Designer must consider 2 points in their mind. They must have exact knowledge of standards that where have to be applied. Second, they should follow strictly. PCB sizes. Mechanical stress. A small PCB with size of less than 100 by 150 and thickness of 1.6 mm. Care is needed for bigger size boards. Heavy device parts should be mounted near supporting devices like card guide and connector. Other board size connectors. Electrical functioning. Same circuitry should be realized on the same board and same rule. The board size will be disproportionately larger. More space provided for interconnections. Longer interconnections are susceptible to functional disturbances. Small circuit boards are difficult and at a higher cost. It's caused by external interconnections or connections required. Testing and servicing. To enable efficient testing and repair PCB, small size boards should be given preference. In large boards, isolation of parts is not possible because there is usually no means to interrupt signal flow. Faulty card is not easy to detect but easy to repair. Modifications. It is a good practice to utilize the broad area. Wherever useful, there should be a provision to add ICs. Many times, complete design of PCBs might be avoided. In such cases, the design should be modified without minor modifications. Equipment dimensions. PCB design and number dictated by exterior design concept of the equipment. Standard sizes. Ideal board sizes are very large, neither very small. Optimum board size should be 150 mm to 250 mm. Routing rules. The routing rules are a set of rules that are applied when a call is received, and they help to determine how the resulting outbound call is handled. Each routing rule has two sections. The first section contains conditions on inbound properties that must be satisfied for the rule to fire. The second section sets properties that configure the outbound portion of the call. Rework and repair of printed circuit boards. When printed circuit boards are inspected and tested, whether bare or fully loaded, and defects are found, it is necessary to evaluate the cost of effectiveness of the repairing board and at the same time provide the user with same reliability as the original product. In case of simple boards with a few defects, it is usually not economical to rework on them. However, many boards are highly complex and a fully loaded board could be expensive. It may turn out to be more economical to rework on the same so that it will pass all the tests. Approaching components for tests. Most designers provide test points at convenient locations on the circuit board. These points are defined by AC and DC voltages along with the waveform patterns. This is usually a vertical mounted pin to which a test prod can be attached. Procedure of repair and rework PCBs. Remove any assemblies, plugs, wire that will facilitate repair work. Label the component to be removed. Observe carefully how the component has been placed before removing it. Be careful to handle the printed circuit boards by the edges only. Remove the dry film from the soldered joint point that is to be worked on. Heat the repairing surface mounted PCBs. In next few years, it will be hard to find a manufacturer who will build anything that will not contain surface mounted devices. Having the proper tools to do the job and the knowledge to use the tools that you choose will be important to your survival in the electronic repair business. Surface mount technology has been around for a long time, but the tools for removal and replacement of surface mount devices have been slow to be accepted by the service and repair personnel and organizations. Possibly, it was because of the high cost of the tools. Technicians looked for innovative way to use tools at hand to do the work. The justification for investment on the repair and rework stations come from the fact that the high-priced equipment certainly deserve to be treated in a better way so that you are in a position to perform the job worthy of your knowledge and experience. Methods of removing a faulty multi-lead surface mount components are: cut all the leads, heating methods, removal and replacement of surface mount devices. The following steps should be taken to remove a component using a hot gas machine. Apply a small amount of liquid flux to all the joints. Choose the correct head to place the component. With the PCB in place, activate the gas flow to reflow the solder on every joint. If the component has been bonded with an adhesive, rotate the head to shear the bond. Remove the component with a vacuum pickup and allow the PCB to cool. Remove any remaining solder by use of a fine desoldering braid. Allow a further cool down period. Inspect the pads to ensure that they are not damaged. For replacement of the component, the following procedure is followed. The new component should be carefully inspected to ensure that the legs are not bent or distorted. A thin film of flux is lightly applied to the pads. The component is then placed into the head of the hot gas machine and carefully lined up to the PCB. The fingers on the solder quick tape will help to align the component. Before gas flow is initiated, the component should be lifted away from the board surface until the legs are cleared from the pads. The gas flow should then be applied. The gas will heat up the legs and the solder on the pads. When the solder flows, the component should be carefully brought down onto the board, ensuring that the legs of the component are sitting between the fingers of tape and hence are central over the pads. Allow gas flow to continue for a few seconds to ensure that the solder flows correctly around each leg. When the solder flows correctly, switch off the gas and allow the board to cool at least for a minute to avoid disturbing the joints before removing the PCB from the machine. After removing the PCB carefully, remove the solder quick tape and clean all excess flux from the joints. Inspect all joints with a 10x magnifier to ensure correct reflow. Clean the PCB with isopropyl alcohol in the aerosol form to ensure penetration of solvent under the component to wash out any flux. The area can then be brushed to remove all traces of flux. Repairing damaged pads. The most common damage on surface mount boards is lifted pads on quad flat pack layouts. The most probable reason for this is when operators have difficulty in knowing when the solder joints on all four sides of the device packages are molten. The following method is suggested to repair such type of damage. Remove the damaged pad or track and clean the immediate area on the board. Select the appropriate replacement track or pad. Solder the replacement pad or track to the undamaged track on the board. Use an adhesive capable of withstanding high temperature and glue the new pad or track to the PCB substrate. Clamp together until the adhesive has cured. Solder the replacement component in place. Clean off flux residue. Reapply any solder resist that has been removed. Working and serviceable repairs diagrams are shown in figure. Working repair. Serviceable repair. Repairing damaged plated through holes. There are three methods of remaking a damaged through-hole connection on a double-sided board. Through-hole copper plating. This process involves forcing a series of plating solutions through the hole under repair, thus simulating the original plating process. Not suitable for single-piece repair. Fused eyelets. The use of eyelets has been standard in the industry for a number of years. Designed to be form flushed with the circuit board, they overhang on modern circuits where the track spacing is limited. This may pose a constraint on their use. Use of copper bales. Copper bales are made by plating approximately 30 microns of copper into solder wire of different sizes and then overplating to protect the surface solder ability. When positioned in the damaged through-hole formed and fused, the copper bale does not take any more room than the original through-hole plating, and it is undetectable as a repair after component insertion and subsequent soldering. Use of copper bale for repairing damaged plated through holes are shown in figure. An ideal rework station would include a vision system that can be used when placing and soldering the component, a placement tool that will allow for movement that is smaller than the smallest pitch being used on the board, a heating method that can control the heating process and can heat the board and the component in a manner that approximates the method used in the original production. It must be able to apply uniform heat without delaminating the board or damaging the component during the removal or replacement. Facilities that are simple to use both by an operator and engineer without much training. Soldering procedure. Soldering is the process of joining metal parts by making use of any of the various fusible alloys whose melting temperature is lower than that of the material to be joined, and where by the surface of the parts create an intermolecular bond without becoming molten. Soldering process involved in melting of the flux, which in turn remove the oxide film on the metal to be soldered. Melting of the solder, which makes the lighter flux and brings the impurities suspended in it to the surface. Partial dissolution of the sum of the metal in the connection by the solder. Cooling and fusing of the solder with the metal. Quite often, for locating a problem in the functioning of a circuit, it is necessary to remove components from printed circuit boards and carry out the requisite tests on it. The process of repairs usually involves disassembly of the particular component, testing of the component, replacement of the component found defective, testing the circuit for performance check. Theory of soldering. It is essential to understand the theory of soldering so as to visualize as to what happens when the soldered joints are formed. Soldering is not a single physical attachment of one metal to another, but it chemically forms an intermolecular bond. There are a number of variables in soldering process which would be controlled for proper soldering process. The welting action. When hot liquid solder dissolves and penetrates the metal surface to be soldered, it is referred to as wets the metal. The molecules of solder and say copper blend to form a new alloy, one that is part copper and part solder. It is a solvent action which is called wetting that forms intermolecular bond between parts and intermolecular compound. The forming of a proper intermolecular bond is the heart of soldering process that determines the quality and the strength of the solder joint. Wetting can only occur if the surface of the copper is free from contaminators and any form of oxide film that forms when the metal is exposed to air. Solder and work surface needs to have reached proper temperature. Surface tension. We are familiar with surface tension of water as a force that retains the cold water in globules on a greasy plate. The adhesive force that tends to spread the liquid on the solid is in this case less than the cohesive force. Washing with warm water and using a detergent reduces the surface tension, and water wets the greasy plate and flows out into a thin layer. It happens if the adhesive force is stronger than cohesive force. The cohesive force of a tin solder is even higher than that of water and also draws the solder into spheres as it tends to minimize the surface area. Flux acts similarly as the detergent does with the greasy plate. Further surface tension is highly dependent on any contamination on the surface as well as on temperature. Only if addition energy become much stronger than the surface energy, ideal wetting will occur. Creation of an intermetallic compound. The intermolecular bond of copper and tin forms crystalline grains whose shape and size is determined by the duration and the intensity of the temperature while soldering. Less thermal application results in fine crystalline structures, which results in excellent solder joints having an optimum strength. Longer reaction times provided by either longer time or higher temperature or both result in coarse crystalline structures having less shear strength because of being more gritty and brittle. With copper as the base metal and tin or lead as solder alloy, lead does not form any intermetallic compound with copper. However, tin penetrates into copper, and the intermolecular bond of tin and copper forms the intermetallic compounds at the interface of solder and the metals being joined. The intermetallic layer must be very thin. In laser soldering, the intermetallic layer has a thickness of the order of 0.01 mm. In wave soldering and manual soldering, the thickness of the intermolecular bond of excellent solder joints mostly exceeds 0.5 micrometer. The shear strength of the solder joints decreases with an increase in the thickness of the intermetallic layer. The attempt is always made to keep the thickness less than 1 micrometer. This can be achieved by keeping the soldering time as short as possible. The wetting angle. The ability of a surface to be wetted by solder can, to some extent, be assessed by the shape of the meniscus formed when a drop of solder is placed on the hot flux surface approximately 35 degrees Celsius above the eutectic point of the solder. If the meniscus has a noticeable undercut edge, like a water drop on a greasy plate, or even if it tends to form balls, the metal is not all solderable. The solder ability is good only when the meniscus draws out to be a fine angle of less than 30 degrees. Required tools for soldering. Before going to learn about soldering techniques, we should learn about tools required for soldering. Variable temperature soldering iron, used for applying heat to joints during the soldering process. Damp sponge. It is used for cleaning the soldering iron tip. Rosin core solder. It is used to electrically and mechanically bond a component to the PCB. Wire cutters or side cutters. It is used for trimming component leads and stripping insulation from wires. Needle nose pliers, used for holding, placing and shaping components. Desoldering pump and or desoldering braid for removing solder. Scotch tape and or a third hand for securing components. Safety glasses. For eye protection, these are mandatory in the lab. Magnifier To provide more detail during intricate work, a magnifying glass is convenient, but an illuminated magnifier is better. Light source to prevent eye strain. Ventilation to extract and dispel fumes generated during the soldering process. Flux to clean components and PCB pads. Acid brush to assist in the removal of flux residue. Important soldering tips. The following tips provide a quick guideline on how to make proper joints. Cleanliness. All parts, including the soldering iron tip, must be clean and free from grease, oxidation, and contamination. Solder does not over contaminated areas. Moreover, solder is repelled by dirt. Severe contamination is evident when solder begins to bead. A common source of contamination is oxidation. Old components and copper boards will often have an oxide layer that prevents a good solder joint. Ensure all components have shiny leads and the PCB has clean traces. An abrasive such as blue or pink eraser, emery paper, or steel wool can be used to remove the oxidized layer from the PCB board and the components. Tinning. In addition to being clean, the soldering iron tip must also be tinned, coated with solder. Tinning the tip allows the solder to flow on the components more quickly rather than soldering iron tip itself. Tinning involves adding a few millimeters of solder to the tip and then wiping and rotating the tip on the damp sponge to reveal a shiny surface on the tip of the soldering iron. A thin layer of solder will coat or tin the tip of the solder iron. When done soldering, thinning the iron is required to protect the tip from oxidizing, thereby dramatically increasing its life. Temperature. Ensure that both the component leads and the PCB's copper layer are heated at the same time. Soldering iron tip should be in contact with both the component and the PCB pad. This will ensure that each surface is relatively close in temperature, resulting in a good joint. If there is a temperature difference between the two surfaces, the solder will form a dry joint. Soldering irons are typically set around 650 Fahrenheit, depending on the lead-tin ratio of the solder being used. Too much heat causes excessive sputtering of flux, and too little does not melt the solder in a timely manner. Duration. The duration that the iron is in contact with the component and the PCB is dependent on the size of the joint and your soldering iron temperature. For the typical PCB through-hole joint, it should take a few seconds to heat the joint and apply the solder. This will require practice, so do not expect to be fast if you are a beginner. Excessive heat, several seconds in duration, will damage sensitive semiconductors. If this is a concern, use a heatsink attached to the component leads, sometimes as simple as an alligator clip. These concerns can sometimes be avoided by soldering sockets instead of the semiconductor itself. Adequate solder coverage. If too little solder is applied, the joint will not make a secure connection and will cause erratic behavior. However, if too much solder is applied, the joint may bridge with adjacent joints, resulting in electrical shorts. Precautions. Soldering irons get very hot. Please ensure you follow precautions during use. Basic safety precautions are listed below. Never leave your iron turned on while unattended. Turn the soldering iron when it is not being used. If the iron is left on for long periods of idle time, the soldering iron tip will be destroyed through oxidation. Eye protection must always be worn when soldering. Hot flux can spit up and into an unprotected eye. In the capstone design lab, use of eye protection is mandatory. If the cord of the soldering iron is damaged, inform the lab staff who will ensure it is replaced.
Never set the soldering iron down on anything other than an iron stand.
To prevent burning your fingers, use needle nose pliers, heat-resistant gloves, or a third hand tool to hold some small pieces.
Familiarize yourself with the safe handling of all materials used during the soldering process.
This includes solder, flux, alcohol, and desoldering braid. Each has a material safety data sheet (MSDS) and can be found in the lab or online. Safe operating procedures are found posted on the wall close to the soldering facilities. How to solder through-hole components. Most of the soldering done in the capstone design lab is through-hole. A through-hole joint is a type of soldering joint in which the components join with the PCB pad through a physical hole in the board. The following steps will illustrate how to make a proper through-hole solder joint
on a PCB.
Ensure that the printed circuit board and all the components are clean. Cleaning can be achieved with a mild abrasive
and or by the application of flux.
Plug in the soldering iron, turn it on and let it warm for 2 to 3 minutes. Wet the soldering station sponge with water provided in the lab. Do not wet the sponge in the bathroom or the water fountain. Clean the tip of the soldering iron and tin it with solder. Insert the component into the holes. Ensure that the component is secure by taping the component or by using a third hand. This technique, however, is not recommended for two-sided boards as the flow of solder to the component side is restricted. Apply soldering iron tip to one side of the joint, making contact with the component lead and the board copper foil, ensuring that both are heated up to the same temperature as shown in figure. Slowly add a few millimeters of solder to the other side of the joint. Do not apply solder to the soldering iron tip. If enough heat was applied to the PCB pad and the component wire, the solder will flow freely onto the joint. Method of soldering through hole joints as shown in figure. Remove the solder when the joint is suitably covered. If the PCB is double-sided, the solder should flow through the hole around the component lead and make a bond on the component side of the board, opposite to the side that the solder was applied. If this wicking does not occur, the hole may be undersized. Clinching could be blocking the solder's path,
or the component lead is not clean.
Remove the soldering iron and allow the joint cool naturally. Cut the lead of the component if necessary, as shown in figure. How to solder surface mount components. Surface mount soldering requires more experience and skill than through-hole. It is recommended that one practices with through-hole prior to attempting any surface mount soldering. As the name suggests, the surface mount involves soldering a component to either the top or bottom surface of the PCB.
Depending on the footprint, the pads are usually spaced closer together, finer pitch, making the soldering more susceptible to solder bridges, etc.
The actual soldering of the joint is similar to that of through-hole method.
One difficulty, however,
is maintaining the parts alignment on the PCB pads. A good technique is outlined here. Align the component on the PCB pads. This can be aided with use of tweezers and dental picks. Secure the component on the PCB by applying a small amount of pressure onto the top of the component using a small slot screwdriver. An index finger resting on the end of the screwdriver provides enough force to secure the device. Solder one of the corner components leads to the PCB pad. Align the remaining pads and solder the opposite corner PCB pad. Solder the remaining pads in a pattern that does not build up too much heat in the device. Desoldering technique.
Desoldering may be required for several reasons. A component may have failed, a wrong part was installed, a design modification necessitates a change, or if a board contains expensive components that can be salvaged. Whatever the reason, there are three main common techniques to remove solder from a joint: using a desoldering pump, a desoldering wick, or desoldering iron. Regardless of the method used, if it is permissible to destroy the part during removal, then a lot of time and effort can be saved. For instance, using wire cutters to trim off all the pins of a through hole IC so that they can be removed individually makes the removal process much easier. In most cases, avoiding damage to the PCB is of paramount importance. Solder pump. A desoldering pump is exactly what it sounds like, a pump that sucks up solder. Usually the pump is spring-loaded and provides a recoil when released. The 4 steps below outline how to desolder a joint using a desoldering pump. Prime the desoldering pump. This involves depressing the desoldering pump spring. The pump will click and then correctly depress. Heat the joint from one side with a soldering iron tip. Wait 1 to 2 seconds until the solder begins to melt from the soldering iron heat. Put the pump tip on the other side of the joint. Do not be afraid to actually touch the joint. Press the desoldering pump spring release button to suck up the solder. This procedure should be repeated if the joint has a significant amount of solder. If done correctly, the joint should eventually look as shown in figure. Desoldering braid or wick. A desoldering braid removes solder from a joint using a technique known as wicking. Desolder braid is a piece of material that sponges up molten solder by capillary action that draws out solder away from the joint, the braid. The following procedure outlines the basic steps involved in desoldering a joint using desoldering braid. Place the desoldering braid over the joint. Press the desoldering braid onto the joint with a soldering iron tip. This will apply heat to the desoldering braid and the joint, allowing the molten solder to flow. Wait for the solder to melt. The solder should flow onto the braid and away from the joint. Cut off the solder coated portion of the desoldering braid. There should be no copper visible in the portion that is removed. Braid is a very expensive desoldering iron. Desoldering iron. Using a desoldering iron available with higher end soldering stations is similar to using a solder sucker. The desoldering iron is essentially a soldering iron with a built-in vacuum. Make contact between the iron and the joint to be desoldered, ensuring the vacuum opening is not blocked. Once the solder joint has become molten, depress the button on the iron to activate the vacuum. It is very important for the life of the desoldering iron that the vacuum assembly be cleaned after every session of use. As with a normal soldering iron, the desoldering iron tip should be tinned before and after every use. Removing components. To remove a component with little or no damage to the PCB, a component takes practice and patience. Often when removing a component, PCB pads and tracks may be damaged by lifting of the board. Below are some tips that may be useful when removing components from a PCB. Desolder all joints pertaining to a component prior to removal. It may be necessary to go over the joints several times before all the solder is removed. Practice patience. Use pliers and gently pull on components while applying heat to the joints. Do not pull with force because the PCB pads and the tracks will be damaged. Do not try and remove components by prying them.
Do not try to push the component out of the holes with the soldering tip. This will certainly lift the copper pad of the PCB and ruin the iron tip. In order to get better thermal conductivity between the iron and the solder joint, it is sometimes effective to add a small amount of solder. Study of documentation in design and fabrication. Documentations. Scope. In small-scale industries, the circuit diagram engineer must have knowledge about the layout. Documentation in this case will probably have few sheets with some notes. There will hardly be any information problem or communication problem. Documentation must be handled by the right person. It varies place to place. Small companies go for minimum essential while large companies has exact laid out forms, lists and files. It must contain all information about layout. Layout design must provide all information for completion of circuit work. Circuit diagram. Circuit diagram must be considered. Connectors, critical signal paths, heat sources. Connectors. Input and output connections must be predetermined by location on locator or connector. It must be clearly marked with connectors. Critical signal paths. Length should be minimum and conductors should be guarded by ground lines. Heat sources. Components releasing considerable heat to be identified in the circuit diagram to avoid heat transfer on the board to sensitive components. Component list. For simple circuits, they do not have separate component lists. The component specification incorporated with circuit diagram. Component list should be prepared by circuit designer with all requirements of circuit components. Component list, depending on needs, it may include component code, exact specification, supplier, price, selection criteria, matching requirements, mechanical dimensions. Layout sketch. The end product of layout designing is the pencil sketched component and a conductor drawing, which is called layout sketch. It has relevant information about the preparation of layout. Layout sketch should include information such as component holes, conductor width, minimum spacing. Layout coding example as shown in figure. Mechanical drawing. Mechanical drawing is very important for documentation for the mechanical fabrication steps of PCB. It includes processing of boards. Mechanical drawing informations. Board outlines with tolerances. PCB laminate to be used. Plating specifications. Registration and mounting of holes. Assembly drawing. It includes the component list and provides all information about correct assembly of components in the particular board. It shows board and component outlines. Component outlines must be submitted with the component outline codes. Prototype board assembly consists of blueprint of PCB boards. PCB fabrication. Printed circuit board fabrication. A PCB consists of two basic parts: a substrate, the board, printed wires, the copper traces. The substrate provides a structure that physically holds the circuit components and printed wires in place and provides the electrical insulation between conductor parts. A common type of substrate is FR4, which is fiberglass epoxy laminate. It is similar to older types of fiberglass boards but is flame resistant. Substrates are also made from Teflon, ceramics, and special polymers. PCB cores and layers stack up. During manufacturing, the PCB starts out as a copper-clad substrate. Rigid substrate is a C-stage laminate, fully curved epoxy. The copper cladding may be copper that is plated onto the substrate or copper foil that is glued to the substrate. The thickness of the copper is measured in ounces (oz) of copper per square foot, where 1 ounce per square foot of copper is approximately 1.2 to 1.4 mils, 0.0012 to 0.0014 inch thick. It is common to drop per feet square and refer to thickness only in ounce. For example, you can order 1 ounce copper on a 18-inch thick FR4 substrate. A substrate can have copper on one or both sides. Multi-layer boards are made up of one or more single or double-sided substrate called cores. A core is a copper-plated epoxy laminate. Cores are glued together with one or more sheets of a partially covered epoxy. Developed photoresist on copper, as shown in figure. Photolithography and chemical etching. Selectively removing the copper with etching process requires etching the unwanted copper while protecting the wanted copper from the etchant. This protection is provided by a polymer coating called photoresist that is deposited onto the surface of the copper cladding as shown in figure. The photoresist is patterned into the shape of the desired print circuit through a process called photolithography. The patterned resist protects selected areas of the copper from the etchant and exposes the copper to be etched. There are two steps to photolithography: patterning the photoresist, exposing the resist to light, typically ultraviolet light, and developing it, selective removal in a chemical bath. There are two types of photoresist: positive resist, negative resist. When positive resist is exposed to UV light, the polymer breaks down and can be removed from the copper. Conversely, negative resist that is shielded from UV light is removed. A mask is used to expose the desired part of the photoresist. A mask is a specialized black and white photographic film or glass photoplate on which a picture of the trace and pads is printed with a laser photoplotter. The mask is placed on top of the photoresist as shown in figure. The dark areas block UV light and the white transparent areas allow the UV light to hit the photoresist, which imprints a circuit image into the photoresist. A separate mask is used for each layer of a circuit board. CAD layout generates the data that the photoplotter uses to make these masks. Resist CU substrate. Another way of exposing the photoresist is by using a programmable laser to draw the pattern directly onto the photoresist. This is a newer technique called laser direct imaging (LDI). A benefit of the LDI process is that it uses the same data as the photoplotters, but no masks are required. After the photoresist has been exposed, either with the mask and UV or with the laser, it is washed in a chemical called the developer. In the case of positive resist, the resist breaks down during exposure and is removed by the developer. In case of negative resist, the UV light cures the resist and only the unexposed resist is removed by the developer. Common developers are sodium hydroxide (NaOH) for positive resist and sodium carbonate Na2CO3 for negative resist. Once the resist has been exposed and developed, a circuit image made of the photoresist is left on the copper. Next, the board is etched in an acid solution such as ferric chloride FeCl3 or sodium persulfate Na2S2O8. The etching solution does not significantly affect the photoresist but attacks the bare copper and removes it from the substrate, leaving behind the resist-coated copper. Some processes use a plated tin alloy as the etch resist. The tin alloy plating is more resistant to etchants and pre-prepares the copper surface for solder processes. In this case, the photolithography processes are used to selectively plate the circuit pattern onto the copper surfaces prior to etching. When polymer etch resists are used, the photoresist is cleaned from the copper with a resist stripper, leaving behind the copper traces. When metal etch resists are used, the plating is typically left in place. Holes of the leads, etc., are not etched into the pads because they are drilled after all of the cores have been glued together later in the process to ensure proper alignment of the holes between board layers, as shown in figure. Mechanical milling. As mentioned above, milling is an alternative to etching. To mill the board, a computer numerical control machine is programmed with a digital map of the board and grinds away the unwanted copper. The unwanted copper can be completely removed, or just enough copper may be removed to isolate the pads and traces from the bulk copper. Removing only enough copper to isolate the traces from the bulk copper reduces milling time but can affect the impedance of the traces. Layer registration. After the inner layers have been patterned, the cores are aligned, called registration, and glued together. Registration is critical because the pads on each layer need to be properly aligned when the holes are drilled. Registration is accomplished using alignment patterns called fiducials and tooling holes in the board which slide onto guide pins. With the cores in place and properly aligned, a heated press cures the assembly. After the assembly is cured, holes are drilled for a through-hole component leads and vias. The drilling process inevitably heats the laminate due to friction between the laminate and the high-speed drill bit. This tends to soften the laminate and smear it across the walls of the drilled copper. After the drilling process are finished, the assembly is placed into a bath to etch back the laminate slightly and clean the faces of copper pad walls. This is called laminate etch bath or dismear. Once the holes have been drilled and dismeared, a physical path exists between the pads on different layers. To make electrical connections between pads on different layers, the board is placed into a plating bath that coats the inside of the holes with copper, which electrically connects the pads, hence the term plated through holes. The plating thickness varies but is typically about 1 mm, 0.001 inch thick. The cutaway view of figure shows a plated through hole on an internal layer of PCB. The top and bottom copper is actually patterned after the plating process is finished, because the plating process would replate the areas where copper has been removed. Not all layers have traces. Some layers are planes. See figure. Plane layers are typically used to provide low impedance, resistance and inductance connections to power and ground, and to provide easy access to power and ground at any location on the board. Plane layers and leads of components are connected to ground or power by soldering them into plated through holes. Since copper conducts heat well, soldering next, a thin polymer layer is usually applied to the top and bottom of the board. Holes are drilled into the board and then copper plated. A. Non-plated through hole. B. Plated through hole, as shown in figure. A connection to a plane layer through a thermal relief, as shown in figure. A clearance area provides isolation between plated hole and a plane, as shown in figure. This layer the polymer using photolithography to expose the pads and holes where components will be soldered to the board. The solder mask protects the top and bottom copper from oxidation and helps prevent solder bridges from forming between closely spaced pads. Sometimes openings in the solder mask are not made over small or densely placed vias called tenting a via. Tented vias are protected from having chemicals such as flux from becoming trapped inside the hole. Tenting also prevents solder migration into the hole, which could lead to poor solder joints on small components that are close to and connected to the via. Finally, markings called the silk screen are placed on the board to identify where components are to be placed. PCB design. Initially, PCBs were designed manually by creating a photo mask on a clear mylar sheet, usually at 2 or 4 times the true size. Starting from the schematic diagram, the component pin pads were laid out on the mylar sheet and then traces were routed to connect the pad. Rub-on dry transfers of common component footprints increased efficiency. Traces were made with self-adhesive tape. Pre-printed non-reproducing grids on the mylar assisted in layout. To fabricate the board, the finished photomask was photolithographically reproduced onto a photoresist coating on the blank copper-clad boards. Nowadays, PCBs are designed with dedicated layout software, generally in the following steps. Schematic capture through an electronic design automation EDA tool. Card dimensions and template are decided based on required circuitry and case of the PCB. The position of the components and heat sinks are determined. Layer stack of the PCB is decided with 1 to tens of layers depending on complexity. Ground and power planes are decided. A power plane is the counterpart to a ground plane and behaves as an AC signal ground while providing DC power to the circuits mounted on the PCB. Signal interconnections are traced on signal planes. Signal planes can be on the outer as well as the inner layers. For optimal EMI performance, high frequency signals are routed internal layers between power and ground planes. Line impedance is determined using dielectric layer thickness, routing copper thickness, and trace width. Trace separation is also taken into account in case of differential signals. Microstrip, strip line, and dual strip line can be used to route signals. Components are placed, thermal consideration and geometry are taken into account. Vias and lands are marked. Signal traces are routed. Electronic design automation tools usually create clearances and connections in power and ground planes automatically. Gerber files are generated for manufacturing.
The transmission convergence sublayer. The transmission convergence sublayer is responsible for the following. Cell delineation maintains ATM cell boundaries, allowing devices to locate cells within a stream of bits. Header error control sequence generation and verification. Generates and checks the header error control code to ensure valid data. Cell rate decoupling. Inserts and suppresses idle, unassigned ATM cells to adapt the rate of valid ATM cells to the payload capacity of the transmission system. Transmission frame adaptation. Packages ATM cells into frames acceptable to the particular physical layer implementation. Transmission frame generation and recovery. Generates and maintains the appropriate physical layer frame structure.
Types of PCB: single-sided, double-sided, multi-layer, and flexible. PCB types. PCB types: single-sided, double-sided, multi-layer, and flexible. Single-sided layers PCB. The most basic PCBs have the components mounted on one side of the board and conductor pattern on the other side. Because there is only a conductor pattern on one side,
this type of PCB is called single-sided or single layer.
This type of circuit board is suitable for simple circuits only. Because there is only one side, no wires can cross and they have to be routed around each other. Double-sided layer PCBs. Double-sided or double-layer printed circuit boards (PCBs) are better suited to complex circuits as they have twice the area of the conductor pattern compared to single-sided PCBs. Double-sided PCBs have a conductor pattern on both sides of the board.
Having two separate conductor patterns requires an electrical connection between them.
Such electrical bridges are called vias. A via is simply a hole in the PCB that is filled or plated with metal and touches the conductor pattern on both sides. Multi-layer PCBs. Multi-layer PCBs have one or more conductor pattern inside the board to increase the area available for wiring. This is achieved by gluing or laminating several double-sided circuit boards together with insulating layers in between. The number of layers is referred to as number of separate conductor patterns, usually even and including the outer two layers. Most boards have between 4 to 8 layers, but PCBs with almost 100 layers can be made. Since the layers in a PCB are laminated together, it is often difficult to tell how many are there, but if you inspect the side of the board closely, you might be able to count them. Large supercomputers often contain boards with plenty of layers,
But since it's becoming more efficient
to replace these computers with a cluster of ordinary PCs,
high layer counts are now less common.
vias in multi-layer PCBs. The vias described in double-sided PCBs always penetrate the whole board. When there are multiple layers of conductor patterns and you only want to connect some of them, vias waste space that could be used to route other wires. Buried and blind vias avoid this problem because they only penetrate as many layers as is necessary. Blind vias connect one or more of the inner layers with one of the surface layers without penetrating the whole board. Buried vias only connect inner layers so you can't see them by looking at the surface of the PCB. Flexible.
Single-sided flexible circuits have a single conductor layer made of either a metal or conductive metal-filled polymer on a flexible dielectric film.
Holes may be formed in the base film to allow component leads to pass through for interconnection, normally by soldering. Single-sided flex circuits can be fabricated with or without such protective coatings as cover layers or cover coats. However, the use of protective coating over the circuits is the most common practice. One conductive layer, either bonded between two insulating layers or uncovered on one side. Access holes to conductors may be on either one or both sides. Double-sided flex PCBs. Double-sided flexible circuit consists of double-sided copper-clad material with top and bottom cover films, PI or green/yellow oil, carbon ink, etc. Two conductive layers with an insulating layer between. Outer layers may have covers or exposed pads.
The cover films are pre-routed to access copper from both sides
using plated through holes, PTH. Access holes or exposed pads without covers may be on either side or both sides. Vias can be covered on both sides. Multi-layer flex circuit. Multi-layer flex circuit is a combination of single and or double-sided flexible circuits laminated with thermoset adhesive onto a single and or double-sided FR4 clad material. Three or more flexible conductive layers with flexible insulating layers between each one. Outer layers may have covers or exposed pads. Plated through holes provide connection between layers. Access holes or exposed pads without covers may be on either side or both sides.
Vias can be blind or buried.
Plated through hole are shown in figure. Non-plated through hole are shown in figure.